Right, so hello everyone. First of all, why is it that I'm covering two problems in one talk? The answer is that first I'm going to show you an algorithm for subsequence matching in grammar compressed strings. And this algorithm is going to depend on a data structure for the tree coloring problem, and to make our algorithm competitive, we'll show you a new trade-off for this problem. So first of all, what is subsequence matching? Imagine you're given a string and a pattern, and say that the pattern is a subsequence of some substring of the input string. Then that substring is an occurrence of the pattern, and the occurrence is minimal if we are not able to shrink the substring without the pattern is no longer a subsequence of the substring. So the reason why I like this problem is that its applications are easy to explain to people that are maybe not a part of our field. Like, for instance, in this example, where we can, for instance, if we have a bunch of patients in a hospital and we maintain a log of the events that each patient has undergone, then we might want to ask a question like, for instance, give me all the patients that are diagnosed with some disease A, and then given some medicine B at least K times before undergoing surgery C, regardless of which other events that happened in between. And this is exactly subsequence matching. What we do is that we set the pattern to A followed by KBs and then C, and then we look for the pattern in our set of patient logs. But in this work, we want to solve this problem on compressed strings, and the compression scheme that we consider is the straight line program, which is basically a grammar, as the one shown here, where if we want to decompress the example that is shown on the slide, we start from the root node, and then we do a left to right traversal, and we get a parse tree where the string that is compressed is on the leaves of this tree. And I like this model also because we can see it as a directed acyclic graph, and I like to talk about nodes and edges instead of production rules and left and right side of the equality sign. So I'm going to stick with that. So here are the results on this topic, and as you can see, clearly, if we measure by the number of parameters, our algorithm is better than previous ones. But more seriously, first of all, the space bound is better for our algorithm because we exploit the word size, and then also our algorithm is output sensitive in a way that makes it faster for few occurrences. The idea behind our algorithm is based on the algorithm for uncompressed subsequence matching, which is pretty straightforward. If we're looking for a pattern P in the string S, we do a left to right scan of the string S, looking for each character of P. Once we've found an occurrence of P, we know that there's an occurrence in, for instance, the prefix of S, but in order to find the minimal occurrence, we do a right to left scan of P, starting from, in this case, the index J, and then we find a minimal occurrence of P, and this algorithm runs in time n times m. And we then repeat this process from, in this case, if ij is a minimal occurrence, we repeat the process from index I plus 1. So this idea we want to adopt to grammar compressed strings. And again, it's fairly straightforward. What we do for each node is that we store a bit string that is a summary of the characters generated by the string, the characters that are in the string generated by the node. So in this case, because this node V generates A, B, B, A, D, we store a 1 because there's an A, a 1 because there's a B, and then a 0 because there's no C in the string, and a 1 because there's a D. And then when we look for the pattern, say we are looking for the character C, while we are in this node, we can use the summaries to determine that we should not consider any of the nodes in this part of the straight line program, but go directly to this part. And then using this, we achieve an algorithm with this running time where this term stems from creating the summaries, and this is for looking for each of the characters of the pattern, for each occurrence of the pattern. And here I should say that h is the height of the straight line program. This is basically the algorithm. The rest of the talk is going to be about how to bound the parameter h to something that is a bit more interesting. So the first step of the new algorithm is to make a heavy path decomposition of the straight line program. So what we do is that for each node, we choose the outgoing edge that leads to the node that generates the longest string as a heavy edge. Normally when we do this for trees, if you know the heavy path decomposition for trees, what we get is a set of disjoint paths. But when we do it for DAGs, what we get is a set of disjoint forests, trees, a set of disjoint trees, and we call this the heavy forest. This forest is upside down, and this is sometimes a bit difficult to grasp, but this forest is upside down compared to the SLP. So that means the forest is actually rooted, or the trees of the forest is rooted in the leaves of the SLP. So if we go down in a tree, we actually go up in the straight line program, and vice versa. The main property of the heavy path decomposition is that on any path in the SLP from the root to some leaf, we visit at most log n trees. So here's the main idea, and this is perhaps the most cluttered figure today, but all of these nodes are part of, I'm going to try to explain this. All of these nodes are part of the SLP. All of the edges are also part of the SLP, but only the solid ones are a part of this specific tree in the heavy forest. So on some path, so we want to do the same thing as we did, as I told you before, with the basic algorithm, and on some path from the root to a leaf, we're going to enter this heavy tree. And say we enter it in this, we enter the tree in this node. Now we want to find an exit point from this tree. So we need to find among these nodes which one of these that generates the character that we're looking for. Actually, we're looking for the first one of these that generate the character that we're looking for. And if none of them does, we need to check if the root of the tree generates the character that we're looking for. Again, if it doesn't, we need to find the last one of these that generate the character that we're looking for. So actually, this turns out to be the tree coloring problem. So because we can color the nodes of the tree with colors that are equal to the summaries that I showed you before. If we do a summary of the characters generated by this node, this will also be the colors of this node, and so on. So in the first step of the algorithm, when looking for the first one of these one that generates the character that we're looking for, it's the it's a first colored ancestor query that we want to make. And this is then, if it's not in any of these or the root, when looking for the character in these ones, it's a last colored ancestor query that we need to make, which is a new thing we define in this work. So basically, given a data structure that solves the tree coloring problem with this addition that we want to support last colored ancestor queries, we get an algorithm for subsequence matching that runs in this time, where P is the pre-processing time of the tree coloring data structure, and Q is the query time, and S is the space of the tree coloring data structure. So now I move on to talking about tree color problems. So a bit more formally, we want to support two queries in our tree color data structure. One is the first colored ancestor, where we, given a node, want to find the first lowest ancestor that has the color that we're looking for. And similarly for last colored ancestor, we're given two nodes, where one is an ancestor of the other, and we want to report the highest node on that path with the color that we're looking for. We can solve this problem in a straightforward manner using T times sigma space. T is the number of nodes in the tree. And also T times sigma pre-processing time, then we get constant query time. A bit more complicated solution is this next one, which depends on the accumulated number of colors that we give the trees. The only problem is that in our case, this easily becomes T times sigma. So this was not useful in our case, which is why we moved on to coming up with a new solution. Okay, so our solution is a two-level solution, and that means that we convert the tree into a binary tree, and then we partition it into clusters. So now we have a tree that is comprised of the boundary nodes of the clusters, and we want to make a solution for that tree, and then also come up with a solution for the actual subtrees that are the clusters. And the way we do the clustering is that we want the clusters to have size order of W, and just to remind you what W is, it's the word size. The solution for the tree that is comprised of boundary nodes is an extension of the straightforward solution that I told you about before. But we need to do a little bit more work to be able to support last colored ancestor queries. So what we do is that for each color in the tree, we make a subtree that is obtained by deleting the nodes that does not have that color. So for instance, in this example, we delete all the nodes that are not blue. And now the problem kind of reduces to first colored ancestor queries, because if you want to make that was maybe a bit too rushed. We also need to apply to the induced colored subtrees, we apply a last colored leveled ancestor data structure, which answers leveled ancestor queries in constant time. So now what we need to do is, if we want to find the last colored ancestor of U and V, then we do from U and V, we do a first colored ancestor query to find their first colored ancestors, which is in this case this one and this one. And then in the induced colored subtree, this is equivalent to this node and this node. And then we can, using the leveled ancestor data structure, we can find the last colored ancestor on this path. In this case, it's this one. So this data structure uses T times sigma over W space, because we only did it for the tree that is comprised of the boundary nodes, and we have t over t divided by w of these. So this becomes the space, and the query time is constant. For the clusters, we propose two new solutions. One is to make the traditional heavy path decomposition of the tree, and then for each path we store, again we use these bit summaries. In this case we store a summary for each node telling us if there is a node on the path from the specific node to the root of the heavy path that has the color that we're looking for. And then also we do we do summaries that allows us to do binary search on the path. So using this, we can support first and last colored ancestor in log w query time, and the same space as before. And the reason why it's log w query time is because this is for clusters of size w. So since we only do binary search, it's becoming log w. Right. The other solution is to assign the nodes post-order indices, and then we store a bit string for each node in a tree that indicates if a node has some specific color, in this case C, and also for each node in the tree we store a bit string indicating the ancestors of that node. And if you want to find the first colored ancestor, we use these two bit strings for the specific node and AND them, and then we get a bit string telling us which of the ancestors that have the color that we're looking for, and all we need to do now is to find the index of the least significant set bit in that resulting bit string. This gives us again a data structure with this space bound and the constant query time, but the pre-processing time is a little bit more due to somewhere along the lines in the construction we need to do we need to transpose. Thanks. We need to transpose a matrix of bit strings. Right. So that actually leads me to the end of the talk. The summary is that we have two new data structures for the tree color problem, where and this I didn't mention before, but we assume that the colors of the nodes in the tree are given as bit strings. That's why we call it the packed tree color problem. And then I have showed you an algorithm with a running time and space bound depending on these data structures. So if we plug it in, we end up with a algorithm for the compressed subsequence matching with these two time and space trade-offs. That's all.
Questions? Simon. Maybe you should leave one by him.
So is the amount of working space you use while you're constructing this data structure the same as the final data structure, or do you use more while you're building it?
It's the same. Otherwise, we wouldn't have been able to claim that, because the pre-processing time is a part of our time complexity for the subsequence matching algorithm. So it's the same. Right.
So I'm asking about the space. So the space is the same as well.
Oh, right.
Working space.
Yeah. The working space is also the same.
Thanks.
Other questions? Thank you again then.